In 2 dimensions, perfect shapes never run out. A regular triangle, a square, a pentagon, a hexagon, a shape with 100 equal sides, you can always draw one more. There's no limit. So here's a question that sounds like it should also have no limit. Build the 3-dimensional version, a solid where every face is the same regular shape and every corner looks exactly alike. And how many can you make? Not many. Not 100. Not 20. Exactly 5, and mathematics can prove there will never be a 6th. This is symmetry. Let's find out why. First, let's be precise about what perfect even means here. A regular polygon is simple. Every side the same length, every angle the same size. Triangle, square, pentagon, hexagon, and onward, without end. There is always a regular polygon with one more side than the last, so this family of shapes genuinely never terminates. That's the flat 2-dimensional case, and it's exactly the intuition we're about to break. Push it further. A regular polygon with 50 sides exists, so does one with 500, so does one with 5 million. Nothing in 2 dimensions ever stops this family. Keep that fact in your back pocket, because the 3-dimensional version is about to behave nothing like it. Now lift the same idea into 3 dimensions. A regular polyhedron, sometimes called a Platonic solid, must satisfy 2 rules at once. Every single face has to be the same regular polygon, and at every single corner, the same number of those faces must meet, arranged identically. Both rules, everywhere, no exceptions. It sounds like a small tightening of the 2D rule. It is about to collapse an infinite family down to 5. Picture what breaking these rules would look like. A solid with some triangular faces and some square faces mixed together, or one where 3 faces meet at one corner, but 4 meet at another. Both are real 3D shapes, plenty of them exist. Neither counts as a Platonic solid. The 2 rules together are strict on purpose, and that strictness is exactly what makes the answer so small. Let's start building and see how far triangles alone can take us. Take equilateral triangles, each corner exactly 60 degrees. Gather 3 of them around a single point and fold that point up out of the flat page. The triangles close around the point, and if you keep going, wrap into the simplest possible solid. 4 triangular faces total, 4 corners, 6 edges. This is the tetrahedron, the sharpest, smallest member of the family. Physically, folding means lifting that shared corner up off the flat page while the outer edges of the triangles swing together and zip shut. Do this correctly with 3 triangles, and every edge matches its neighbor exactly, sealing into a rigid little pyramid with no gaps and no overlaps anywhere on its surface. Don't stop at 3. Gather 4 equilateral triangles around one point instead and fold. It still closes up into a rounder, roomier solid. 8 triangular faces, 6 corners. This is the octahedron, the shape of 2 pyramids glued base to base. Same building block as before, just one more triangle per corner and an entirely different solid appears. Compare it side by side with the tetrahedron. Same triangle, same fold and zip idea, just one more triangle crowded into the same corner. The point has less room to pucker, so it rounds out wider and shallower before sealing shut, and the whole solid nearly doubles in face count in the process. Push it one more step. 5 equilateral triangles around a single point, folded up. It still works, barely, closing into a much larger, rounder solid. 20 triangular faces, 12 corners. This is the icosahedron. 3 different solids, built from nothing but the humble equilateral triangle, just by changing how many meet at each corner. 3, 4, 5. So naturally, you'd expect 6 triangles per corner to give a 4th triangular solid. It doesn't, and the reason why is the whole key to this video. Notice how tight this fold has become. With 3 triangles, the corner puckers generously. With 5, the same corner is pulled almost flat. Barely enough spare angle left to seal it. You can feel, just from the geometry, that this family is running out of room to keep going. So why does 6 triangles per corner break everything? Here's the rule underneath all of it. Every angle of an equilateral triangle is 60 degrees. Lay 6 of them flat around one point, edge to edge. 6 times 60 is exactly 360 degrees, a complete circle. The triangles tile the plane perfectly flat, with nothing left over to fold. There's no leftover gap to pull upward into a point, and no overlap forcing it into a dome. Flat in, flat out. To make a genuine corner of a solid, the angles meeting there must add up to strictly less than 360 degrees. That small leftover gap is exactly what lets the point pucker up out of the page into the third dimension. Check the successful cases against this rule. 3 triangles. 60 times 3 is 180 degrees. A gap of 180 degrees left to fold. 4 triangles, 240 degrees, a gap of 120. 5 triangles, 300 degrees. A thin gap of 60 degrees remaining, just barely enough to pucker into the tightly curved icosahedron. Every working corner in this entire family of shapes obeys one single inequality. The angles meeting there must sum to less than 360 degrees, full stop. Euclid himself proved this exact fact more than 2,000 years ago in the final book of his Elements, that these 5, and only these 5, satisfy the fold. Every attempt at a 6th regular solid runs headfirst into the same single inequality, no matter which regular polygon you start from. Apply that same rule to squares and pentagons, and the count runs out even faster. A square's corner angle is 90 degrees. 3 squares around a point. 90 times 3 is 270 degrees, comfortably under 360, with a 90-degree gap to fold. That gap closes into the most familiar solid there is, the cube. 6 square faces, 8 corners. Now try 4 squares around a point. 4 times 90 is exactly 360 degrees again. Flat, just like the 6 triangles. No gap, no fold, no solid. Squares give exactly one shape and then stop immediately. Notice that the cube is the only Platonic solid built from 4-sided faces, the only one where every angle inside it, corner and face alike, is a plain right angle, which is exactly why it tiles your kitchen floor and stacks into boxes so effortlessly, while none of the other 4 solids do. A regular pentagon's corner angle is 108 degrees. 3 pentagons around a point. 324 degrees, under the limit by a slim 36-degree gap. Fold it, and out comes the dodecahedron. 12 pentagonal faces, 20 corners, the most intricate of the 5. Try 4 pentagons instead. 4 times 108 is 432 degrees, already past 360 before you even reach the fold. It doesn't just fail to fold, it can't even lie flat. Pentagons, like squares, give exactly one shape. The difference between these 2 failures matters. 4 squares landed exactly on the flat 360-degree line, a valid but non-folding tiling. 4 pentagons don't even reach that line cleanly. The shapes genuinely crowd into each other before you'd finish placing the 4th one, well past any hope of lying flat, let alone folding. And hexagons. A regular hexagon's corner angle is a full 120 degrees. Just 3 of them around a point already, total 360 degrees exactly, flat, before a 4th is even considered. Hexagons fail on their very first attempt, and every regular polygon with 7 or more sides has an even larger corner angle than that. So the failure only gets worse, never better. The search is completely finished. Triangles contributed 3 solids, squares contributed 1, pentagons contributed 1. 3 plus 1 is 5, and no future shape, however patient you are, will ever add a 6th. That single flat failure at 3 hexagons quietly settles every regular polygon after it too. A heptagon's corner angle is already bigger than a hexagon's, an octagon's bigger still, climbing steadily toward, but never reaching, 180 degrees. Once 3 copies of a shape hit or exceed 360 degrees, more sides only makes that number larger, never smaller. The door doesn't just close on hexagons, it seals shut on every regular polygon that will ever be drawn after them. Before moving on, let's double-check the count a completely different way. There's a separate formula discovered by Leonhard Euler that every convex polyhedron obeys. Vertices minus edges plus faces always equals 2. Test it on the cube. 8 vertices minus 12 edges plus 6 faces. 8 minus 12 is -4, plus 6 is exactly 2. Test the tetrahedron. 4 vertices minus 6 edges plus 4 faces. 4 minus 6 is -2, plus 4 is exactly 2 again. Two completely different shapes, the same fixed answer. Leonhard Euler, an 18th century Swiss mathematician who reshaped huge parts of modern math, noticed this pattern holds for every convex polyhedron imaginable, not just the 5 perfect ones. It's now simply called Euler's formula, and it's one of the most quietly famous equations in all of geometry. Run the same check on the remaining 3. The octahedron, 6 vertices, 12 edges, 8 faces. 6 minus 12 plus 8 is 2. The icosahedron, 12 vertices, 30 edges, 20 faces. 12 minus 30 plus 20 is 2. The dodecahedron, 20 vertices, 30 edges, 12 faces. 20 minus 30 plus 12 is 2. All 5 solids, built from entirely different reasoning about folding angles, land on the exact same invariant. That agreement between 2 independent arguments is strong evidence neither one is an accident. Getting 5 independent solids, 5 completely different vertex-edge-face triples, to all collapse onto the identical number 2 is not something you'd expect from random shapes. It's a strong signal that both the angle-folding argument and Euler's counting formula are describing the exact same small, tightly constrained family from 2 completely different directions. One last secret, the 5 solids come in a hidden set of pairs. Look closely at the numbers. The cube has 6 faces and 8 vertices. The octahedron has 8 faces and 6 vertices. Those counts are exactly swapped. That's not a coincidence. Mark the center of every face of a cube, connect the neighboring dots, and the shape those dots trace out is a perfect octahedron. Do the same starting from an octahedron, and the dots trace a cube. Each shape is hiding inside the other, one step removed. This isn't just a cute numerical coincidence either. It means the cube and the octahedron share the exact same symmetry group. Every rotation that leaves a cube looking unchanged also leaves its hidden octahedron looking unchanged, and vice versa, because one is quite literally built from the skeleton of the other. The same trick pairs the other 2. The dodecahedron has 12 faces and 20 vertices. The icosahedron has 20 faces and 12 vertices, swapped again. Mark the face centers of one, connect them, and the other appears. That leaves the tetrahedron alone, with 4 faces and 4 vertices. Marking its face centers and connecting them produces another tetrahedron, just smaller. It's paired with itself. 5 solids, but really only 3 underlying relationships. The list of 5 wasn't just short. It was exactly this shape and could never have been any other. Count the tetrahedron's own numbers again to see why it must pair with itself. 4 faces, 4 vertices, an equal number of both, the only one of the 5 where that's true. Nothing else for it to pair with, so geometry hands it back its own reflection instead. So the list stops at 5, not from a lack of imagination, but because a single inequality, the angles at a corner, must add to less than 360 degrees, closes the door on every alternative there could ever be. If that gave you a small jolt of, oh, that's why, then that's exactly what symmetry is for. Subscribe, and every week we'll make one more piece of math or science click. And if it did click, our like helps this find the next curious person.